Okay.
because you've got a column row.
Okay. I have to confess that I can't remember which one's supposed to be which, and so then I cheat when the time actually comes to perform the operation. I just put them in the order in which I need them to be so that I could do a proper matrix multiplication of the two. So, oh, that one's that way, that one's that way. And from that I can figure out which one's contra and which one's co. So I don't personally remember the orders until I actually do the operation.
Seems reasonable.
Okay, so all that I've said now is that there could be some sort of generalized field tensor. That's got stuff in it besides the electric field. So, the one way to get at how things have to transform and what's got to be in here is to think about forces. You know, and I started out the discussion last class by talking about the forces on a moving charge due to a current flowing in a wire. And what we looked at was how the current density transforms and how the background charge density of the wire, the stationary charge density transforms, which led to an electric field that appeared to pull the moving charge. That doesn't appear, it does pull the moving charge towards the wire. And that field turned out to be related to what we knew as the magnetic field acting on a moving charge, right? So the way that we analyzed it was in terms of forces. So I'm going to talk a little bit about forces in order to try to figure out what these A's have got to be. So force, unfortunately, I'm not going to write F again. So I'm not talking field right now, I'm talking force. Force, right, is dP dt, as far as we know, all right? And that's, I've just written what could be a 3-vector form up here. In fact, I will. Except I won't write that there for the equation. So the force is dpk dt. And for just an electric field in acting on a charge in its own frame. Let's see. Okay. So I'm going to have a charge moving along through a region with an electric field. The charge is only going to see an electric field in its own frame. That's just something that I'm going to use in order to try to figure out what's going on here. So I'm going to refer to the charge frame, its own frame, as the primed frame. And in that frame, it experiences the force due to an electric field in the primed frame. So in its own frame. In 4-vector notation, this looks like this. No. I'll write that in the field tensor notation first, but in grid. Q, F prime, K, 0. In the charge frame itself, the time is the proper time. So I can write this like this. D tau. That's the proper time. In the particle frame, the particle has no momentum. So the momentum 4-vector looks like this. It's just got energy. And so we can write now, for homework, I'll make you show that this says the same thing as that. Because I left out the steps in my notes. In my
You're
notes.
asking us to do something that you weren't willing to do yourself?
Yes and no. It actually turns out, it not doesn't turn out, I know that Ohanian actually does the steps from here to there, and I could have copied them, but I didn't. So I was even unwilling to copy them, you could say.
So in other words,
No, actually, he doesn't do the steps. I take it back. He writes this down and he says the reader can work it out.
so he's unwilling to do it.
He thinks it's too trivial. He gives half the solution in the solutions manual and then says, well, the rest of it's easy. I've shown you how to do it. Yeah.
Scumbag Solutions Manual.
Okay. So this is in the particle frame. And if I transform that into the lab frame, I get this. Mu, not a gamma, that's a mu. I'm not going to rewrite it. I'll multiply both sides by the momentum 4 vector. And I've got two momentum 4 vectors there. The order doesn't matter. And the only way that this can be true is if F mu is equal to minus F mu. That is that the field vector, the field tensor is antisymmetric. Okay, so we know that the field tensor is antisymmetric from basic arguments on forces, what the forces have to be. We want to make life easy for ourselves, may not be, but we can assume to start out with that all the terms in the field tensor, the transformation terms in the field tensor, are linear transformation terms. That is, it's just something that depends upon velocity that multiplies something else, that multiplies the field, for example. And if that's true, right, and if the field is somehow a first order derivative of the potential, so the field tensor is going to be a first order derivative of the potential 4 vector, right? Then the only a mu nu that we could construct that would work is also the only antisymmetric field tensor that we can construct from a mu nu is this one. D mu, a mu minus So that will be antisymmetric, and that's first order and derivative. And let's see what that gives us when we actually write it all out. And I will attempt to write it out now. F mu nu is equal to 0. That's my first route. I just let myself off easy here because it's antisymmetric. So let's just recognize that over here, I'll write one of them, minus 1 over c dAx dt minus d phi dx, and so on, all right? Just to remind you. Okay, so I'll just put minus and minus down there for those terms that are up there. 0.
What is this matrix again?
This is the field tensor.
Okay.
Now, this term comes out to be curl of A. This is the 3 vector A. I don't know what A is. All I know is that it's a 3 vector. Or rather that it is the other 3 terms of the 4 vector. Okay? Component of the curl in the Z direction minus the component of the curl in the Y direction minus component of the curl in the Z direction, that's that term there, 0 here, curl in the X direction, need one more here, minus curl in the, oh, this is Y, sorry, Y, X, and this one's got to be X as well. So you can check me by making sure that that actually is antisymmetric, and I think I've got them labeled correctly.
You did.
What?
You did. Yeah. We're looking at it.
It's okay. So all of this comes out of the demand that the special relativity, that Laplacian has to be obeyed. The Poisson's equation has to be true in all frames, right? And that the 4 vector has got to transform like whatever that 4 vector is, it's got to transform like CT XYZ, right? And it has to obey charge conservation. And if we do that, we come around to this relationship. This is what the field tensor has to look like. It's forced to be antisymmetric. The only antisymmetric first order equation that we've got is that one, to get the fields out of the potentials, right? And so we end up with this. This gives us the curl. Okay? Now comes the neat thing. Yeah.
And this field tensor is valid for any electric field?
It's valid for any 4-vector potential, which means it's true for the electric fields. But you see there's a time-dependent term that's just come in here, all right? So for the fields that you've learned about so far, there is no time dependence, so this would be simpler. So I'm going to make one substitution, which is a completely arbitrary substitution, which is that I'm just going to name some vector. And because it's the next thing that comes after A, I'll call it B. B is curl A. And that makes this look a lot simpler. Some of those terms we can identify directly from the wave equation, right? And that yields 0, Ex, Ey, Ez electric fields, right? Minus Ex, 0, minus B in Z direction. Ey, this is an X, minus Ey, Ez, 0, Bx.
Is that a minus by?
I'll get to it in a minute, just to make sure. This is minus here. That's not minus. So, using this simplification, at least this begins to look a little bit more mathematical, right? This is now the electromagnetic field tensor, and I will sort of jump ahead here and tell you that B is the magnetic field and E is the electric field. Right, so we were forced by making some mathematical and physical considerations. That is, we convinced ourselves, we didn't do it here, but Ohanian, he convinced us that the field tensor has to be antisymmetric. And that came out of the argument that we had to obey Lorentz transformations and we have to have charge conservation. Right? So we put those considerations together, we come up with some rules that tell us how these components, I didn't write it down here yet, or maybe I erased it. You guys in the back can't see it, so I can write here. A here is equal to phi A1, A2, A3. The A's are unknown. We just said those have to be the components that transform in the right way. And we ended up with relationships between the A's that said that the extra term that comes here in the field tensor, which would be related to the rate of change of the momentum, or the forces that act on the momentum, has to include the curl of A from over there. Okay? Then we just renamed it, and then what we'll find out is what we can do is we can write down, well, what are the forces that actually act on a particle that's moving at some speed through some space relative to an electric field. And if I have an electric field, and then I start moving the particle through the electric field, I get the equivalent of magnetic field forces. Yeah.
Don't we actually measure the H field, and then this B field is another mathematical construct like the D field? Or is it the other way around?
Unfortunately, it actually turns out, this is due to historical identifications. B is the field that that causes the forces. H is a construct.
Ah,
And E is the field that gives the forces, and D is a construct. Okay, yes. I took the hint. Time is up.